PVI. Okay. Again, PV equal to nRT. So P initial, V initial equal to nRT initial. Okay, now we can put in the numbers. 5 times 1 mole. R is 8.314 moles. Joules per mole per Kelvin. And the initial temperature was 273 Kelvin. So you had to add that much heat to 1 mole of monoatomic gas to increase its volume to 3 times its initial volume at constant pressure. $11,340, we'll say 50 joules.
Go ahead.
An engine with an efficiency of 0.3, so it's a 30% efficiency, absorbs 500 joules of heat per cycle. How much work does it perform per cycle? Okay, so the efficiency is work divided by the heat absorbed. And what they're saying is, so if you divide it by the time of a cycle, okay, heat absorbed, okay. So this is the heat absorbed per cycle, that's the work done per cycle. $150 joules per cycle. How much heat does it discharge again? So the heat engine absorbed this much heat, it did this much work, and the rest it threw out. So, and again, you can divide the time per cycle. So QC is 500 minus 150, 350 joules per cycle. Okay, so a coal power plant consumes 100,000 kg of coal per hour and produces 500 megawatts of power, so electricity. If the heat of combustion of coal is 30 megajoules per kg, what is the efficiency of the power plant? Okay, so by the way, this is megawatts, watts is joules per second. Okay, so let's calculate the amount of heat it produces per unit time. 10 to the 5 kg and 30 megajoules per kg, and this is per hour, so 3,600 seconds. So that's how much heat it's producing per second by burning coal. So So we'll absorb that. That's 10 to the 6, 10 to the 12. 3 times 10 to the 12 divided by that. So 3 divided by 3.6. 0.83 into 10 to the 9 joules per second. That's how much heat you're producing. So the efficiency is work or electricity produced. And the amount of electricity you're producing is 500 megawatts, joules per second. Okay. Efficiency is a dimensionless number.
What was the equation you started out with? Without the two numbers plugged into it?
I'm sorry?
What was the equation that you started out with without the numbers plugged into it from the problem?
Oh, no, this is the amount of heat released when you burn coal is just the mass of coal plus, I guess there's no equation, heat per kg, I guess. Well, you're burning this much coal, 1000 kg. 1000 kg, it releases 30 megajoules per kg. So that many kgs of coal are burned, and that's the amount of heat released per kg. So that times that gives you the amount of. All right, so this is equal to, the efficiency is equal to 500 times 10 to the minus 3 divided by 0.83. So 0.5 divided by 0.83. So that's 0.6, 60%. All right, the world's most efficient coal plant is 4%, 40%. No, 40%, 40%. Yeah. So this is not a real number. If a refrigerator discards 80 joules of heat per cycle and its coefficient of performance is 6, what are the quantity of heat it removes per cycle from the coal reservoir and the amount of work per cycle required for this operation? Okay. So QH is 80 joules. The COP is 6. Okay. COP is work done divided by QC. No, QC over W. Okay, so what is it? Part A asks you the quantity of heat it removes per cycle. Okay, so we are given this, so you can calculate QC from here. Okay, so that's how much heat you're removing per cycle. And part B, how much work per cycle. So in your homes, your air conditioning is the biggest hog of electricity, and then the refrigerator and the water heater. An engine operating between heat reservoirs at 20 degrees Celsius and 200 degrees Celsius extracts 100 joules per cycle from the hot reservoir. What is the maximum possible work that the engine can do per cycle? Who does the maximum possible work? Carnot. Very good. Okay. See, you learn if you listen. Okay, so the work you can do is the maximum work you can do is 1 minus Tc by Th into the heat absorbed. Tc is 293 and Th is 473. So let me first calculate the efficiency of this Carnot engine. So maximum work you can get out of this is 380 joules per cycle. And the amount of heat exhausted is so this is the story of all power plants. Nuclear power plants are about 35% efficient. So for every dollar of electricity you produce, you have to dump $2 of heat. So a gigawatt power plant is a large power plant. The Hoover Dam is a gigawatt. So for every gigawatt of electricity you produce, you got to dump 2 gigawatts of heat. So what do you have to do? Where do you dump the heat? A body of water is a good place to dump heat.
I said that.
You said that?
Yeah, I swear to God.
That's where we done
I swear to God.
Sophia, did she say that?
She did. I swear to God.
Did she pay you to say that? And when you see those large chimneys, big fat large chimneys, that's dumping heat into the atmosphere. An ideal gas at 300 degree Kelvin is compressed isothermally to 1/5 its original volume. Determine the entropy change per mole of the gas. Okay. So entropy change is NR, I believe, log E final minus V. Let me make sure of the expression. There you go, this part. Okay, so they want the entropy change per mole. is compressed isothermally to 1/5 its original volume. V final is 1/5 V initial. Okay, so units for entropy are joules per Kelvin. And we found the entropy change per mole, so that's why we have the mole. So what is this negative sign telling you? Yeah, change in entropy is S final minus S initial. So the final entropy is less than the initial entropy.
So this would never happen, because you can't
You
get.
can't have anything greater than the zero.
It's a fridge.
Hmm?
It's a fridge.
Okay, so the entropy of the gas decreased, but the entropy of the surrounding increased by more than that. What you want is the total entropy of the universe to increase.
But
So-
I thought delta S could be, or, no, it has to be greater.
For the whole universe. You are a system whose entropy is decreasing. Life is a system whose entropy is decreasing. Your surrounding is suffering. Yeah. This is a psychologically uplifting class.
Is that true? Are we always losing entropy? Is that like as we age, or is it like throughout the day?
No, you are an organized system. You're arranging atoms and molecules in an ordered fashion.
Sure.
So as you grow, your entropy is decreasing for that system.
Why is it as we grow?
Well, you got to put in more atoms.
Oh, okay.
If you put more Lego pieces together, you're increasing order.
Okay.
And that's what life is doing.
So like the taller you are, do you have less entropy? That's
For that number of molecules, yeah. Mhm. Because what you did was you took these molecules that were random in nature and you arranged them. What is the entropy change of 10 grams of steam at 100 degrees Celsius when it condenses to water at the same temperature? So change in entropy is heat absorbed divided by the change in temperature. But when you go from steam to water, yeah, all right. Okay. So entropy is decreasing. Steam to water, you're going to a more ordered state. Okay, so the entropy of that system decreased, but of course the entropy of the surrounding increases in that process. Ten grams of water minus 10 grams, and it's 540 calories per gram. We'll convert that to joules in a second. 373 degree Kelvin. And 1 calorie is 4.186 joules. So delta S is so the change in entropy is that. And of course, when water turns to steam, you can 10 grams of water turned to steam, then you would increase the entropy of that water by that much. Yep.
If you have a mutation in your body as an
Mm.
adult,
Mhm.
would that increase your entropy? 'Cause the
No.
mutation is in your system.
A mutation is, let's say you replaced A by C. You didn't change the disorder. You didn't
Just
increase this,
swapped it, okay.
and you made the wrong protein, that's all. Instead of,
How do you increase your entropy as an adult?
oh, you go for a run.
Oh. That's boring,
Like,
alright.
nah.
So simple,
Yeah, you be ADHD. That's
okay. Okay, so you're, alright, we're fine.
50 grams of water at 20 degrees Celsius is heated until it becomes vapor at 100 degrees Celsius. So you're heating the water and then vaporizing the water. Calculate the change in entropy of the water in this process. Okay, so change in entropy is change in entropy while heating plus change in entropy for vaporization. While you're heating the water from 20 to 100 degrees Celsius, the temperature is changing, so you'll have to do an integral. When you're vaporizing the water, it's happening at this same temperature, so you don't have to do an integral. Okay. So this is equal to the amount of heat you added. Okay, this is the amount of dq at this temperature. And this was the initial temperature was what?
293.
Very good. You didn't fall in the trap. Okay. So this is the infinitesimal amount of heat you added to warm the water by that much at that temperature. And so you got to add all this while you're warming the water from 20 degrees Celsius to 100 degrees Celsius. And then you converted all of that to steam at that temperature. Okay, so you'll see something interesting. Okay, let's do this. How much? 50 grams of water. Specific heat of water is 1 calorie per gram per degree Celsius. Log T final is 373 over 293 plus 50 grams, and we'll convert it to more SI units in a second. Latent heat of vaporization is what? $540 calories per gram. Okay. And final temperature is 373. Okay, so what is this saying? This is the change in entropy while you're heating the water from 20 to 100 degrees Celsius. This is the change in entropy when you're turning water into steam. So you see, when you're turning water into steam, liquid into steam, that's when most of the entropy change happens. When you're warming the water, not as much heat, change in entropy happens. Why is that?
The gas has more microstates.
Yeah, it has larger volumes, so there's many more ways of arranging the gas molecules. Okay. And you can convert that to joules, just multiply by 4.186. Oh, you guys can do it. All right, I'll do it. A 300-watt heat pump operates between the ground, whose temperature is 0 degrees Celsius, and the interior of a house at 22 degrees Celsius. So what this heat pump is doing is, it's removing heat from the ground and putting it inside the house. So that's what the heat pump is doing. Okay, extracting heat from the ground and putting in your house. What is the maximum amount of heat per hour that the heat pump can supply to the house? Okay, so the maximum would be, COP would be QC over W, how much heat you extract from the ground. And this is equal to QC over QH minus QC. So COP max would be a Carnot heat engine or heat pump. Okay. So max TC TH minus TC. They give you the work done. What is the maximum amount of heat that it can supply to the house? Okay. The amount of heat per second it's extracting from the ground is this is the COP for a Carnot heat pump. This is the amount power of the motor, okay, heat pump, power of them. So this is 300 watts. TC is 273 Kelvin, and TH minus TC is 22 degrees Kelvin. So the coefficient of performance of this heat pump is 12.4. What is the coefficient of performance of your refrigerator at home? 5 or 6. Okay, so this is So you would be extracting 3,723 watts, joules per second of heat from the ground. And the amount you're dumping in per second is this much. That's how much you're dumping inside the house. The total amount of heat you dump in 1 hour is what they want. Okay. 1 hour is 3,600 seconds. So this much heat is what you, okay. All houses have leaks. Okay, so your heat pump will have to work harder. If you have good seals, then your heat pumps and your air conditionings don't have to work as hard. All right, I guess that finishes the problems.